We have now almost reached the end of week 2, and we have just seen our first planning algorithm. Some of you may be a little disappointed that it took so long to get to the first planning algorithm, and for those people, here comes the next planning algorithm. In the algorithm we've just seen, search states are exactly those states that are world states in the planning problem. States are sets of ground atoms. The algorithm then searched forward from the initial state through all the reachable states until it comes across a goal state. The algorithm we will look at next is backward state space search. In this algorithm, we'll start from the goal and search backwards through the state space until we reach the initial state. This is quite straightforward and very similar to forward search, as you will see. We will start by defining two concepts, namely relevance and regression sets. Relevance is really the equivalent concept to applicability, as it tells us which actions we can use to move through our search space. Again, we start with a planning problem consisting of the usual things, namely a state transition system that tells us how the world can evolve, an initial state from which we're moving away, and a goal description which tells us which states are goal states. Then we can say an action A of our action set is relevant for a goal G if the following two conditions hold. Firstly, the goal intersected with the effects of the action must not be empty. This means there must be an element that is in both sets, so there must be an element that is on the one hand a goal and on the other hand an effect of the action. This means the action must contribute to the goal in some way. Secondly, the positive goals of the goal description and the negative effects of the action must not intersect, and the negative goals and the positive effects also must not intersect. This means the goal must not conflict with the effects of the action. Looking at the first case, if we had a negative effect of the action that was also a positive goal, that means this action would delete this goal from our state, so it would no longer hold. The second case is just the other way around. We have a positive effect that adds a negative goal to the state which we don't want. So, an action is relevant for a goal if it contributes to the goal, that's the first condition, and if it does not interfere with the goal in a negative way, that's the second condition. Now we can define the regression set of a goal G for a relevant action A. And as you can see, this is meant to be the inverse of the state transition function gamma. And it is computed as follows. We start off with the original goal, which is a set of ground literals, and we remove all the effects of the action from that goal, and then we add all the preconditions of the action to the goal. Effectively, this computes from a given goal G, we remove all the effects, meaning we remove all those things that have been achieved by the action that we have selected. So we no longer need to achieve this if we execute this action as the last step before the goal. But then we need to have all the preconditions true so that we can actually execute this action. So what this gives us is a new sub-goal. And if we can somehow achieve this sub-goal, then we know that through the action A we can achieve our original goal. Relevance and regression sets tell us how we can move through our state space backward. They tell us how we can, given a goal and a relevant action for this goal, compute a new sub-goal that constitutes a new search state for our backward search. So here is how we can define the successor function for the backward search, which is equivalent to the reachability analysis we did for forward search. We start with regression through a single step from a given goal. This is defined as the set of all those sub-goals, gamma minus 1 GA, so the regression sets, for a relevant action for G, our original goal. To compute this, we start with our original goal, then compute all the relevant actions for this goal, and regress through these actions to new sub-goals. So this is a set of sub-goals that we get as a result. The next step is that we extend this function to take multiple goals as input. So the input is now a set of goals rather than a single goal. And if we regress through 0 states, that means simply the set of goals stays the same. There's no change. if we can go one step backwards in our search from a given set of goals, this is simply the union over all the individual goals, and we regress those through our regression function defined earlier. And then we can apply this for m steps backwards from a given set of goals by simply doing a recursive definition as we did for reachability. So we apply it for one step after we've applied it to m minus 1 steps for the same set of goals. What this means is that from any of the sub-goals that we've computed in this way, we can reach the original goals in exactly m steps. M actions are necessary to go from the sub-goals to one of the original goals. And we can define the transitive closure for this function, which is the set of all regression sets that are possible here. So these are all the possible sub-goals that we can compute from our original goal. This is pronounced gamma backwards, is simply the union over all lengths of plans that we can implement here, where k is the length of the plan, and we compute gamma minus k of our original goal. So for any k from 0 to infinity, this gives us all the sub-goals that are possibly reachable in our search space from our original goal. Now, given these definitions, we can define the search space for backwards search planning. The input to the algorithm is again a statement of a planning problem consisting of a set of operators, an initial state, and a goal description, as before. Then the search problem can be defined by the following 4 components. We start with the initial state for our search. That is not the initial state in our state space, but the goal. So we're searching backwards from the goal. And in our search space, the goal is the initial state. And if the goal is our initial state, that means we need a new goal test for this search space. And this goal test is that the initial state in our problem specification satisfies our sub-goal S. Remember, we move through the search space, or that is the idea, from the goal backwards by computing sub-goals, and S is meant to be one of these sub-goals. Now, if we come across a sub-goal that is satisfied in the initial state, that means we can reach the goal state from the sub-goal according to our regression function just defined. So if our initial state satisfies the sub-goal, we have reached a goal state in our search space. The path cost function remains unchanged. It is simply the length of the plan. And the successor function we'll be using is simply the regression function we've defined in the previous slide. In general, this function takes a sub-goal that we've come across and computes its successors in the search space. So this concludes the definition of the search space for backward search planning. Next, I could show you the backward search planning algorithm in pseudocode, but I won't. The pseudocode would look almost identical to the code defined for forward search, and I'll leave that to you as an exercise to modify that algorithm so that it performs backward search. Now that you understand how 2 planning algorithms work, I'll even give you the idea for a third one. And to introduce this, I'll give you an example. Suppose our goal, our original goal we start from, is that we want the robot to be at location 1. There is one operator in the DocWorker robot domain that can achieve this goal, and that is the move operator for moving a robot R from location L to location M. And we can see that this operator is relevant because it has an effect at Rm, which we can use to achieve our goal at robot location 1. So all the actions that can be relevant for this goal must be of this form, that we want to move the robot from some location L to location 1. But L remains a variable here. So we don't know what this value of L should be. In fact, if you choose the wrong value for L, it may even interfere with the goal, because we also have a negative effect not at RL. In the backward search we've considered so far, we've only looked at actions for regressing goals to sub-goals. So what we could do in our algorithm is simply replace this value L through all possible constants that are of the right type. But if there are many places from which we can move to location 1, that means there are many options, and that increases the branching factor in our search unnecessarily. So what we can do is simply keep this variable as a variable, and that is what is called lifted backward search, which can also deal with partially instantiated operators where not all the parameters of the operators are replaced by actual values. This does reduce the branching factor, but unfortunately it also makes the algorithm a lot more complicated. Keeping variables in a plan is an example of what is sometimes called least commitment planning, where we try to make as few commitments as possible during the planning process, unless we have a good reason for making a specific commitment. We will see a lot more of this type of planning next week. So this concludes the segment on state space search planning. In this segment we have learned a lot about the strips representation for planning. In the strips representation, we have seen a standardized way of representing the internal structure of states, namely as sets of ground atoms. So we have objects that are related by some relations, and sets of these atoms describe what the world state looks like. And then we have defined what the internal structure of operators looks like. Namely, an operator consists of a name with parameters, a set of preconditions, and a set of effects. The effects are often divided into positive and negative effects, or the add list and the delete list. Based on this, we can define strips planning domains, which are simply sets of operators, and we can define strips planning problems, and consisting of a domain, an initial state, and a goal description. And all this we've learned together with a new syntax, the PDDL syntax, for describing planning domains and problems. PDDL is probably the most commonly understood language by planners today. And next, we have seen how forward state space search can be used to solve planning problems. And as a variant of that, we have also seen how we can search the space backwards from the goal to the initial state. Unfortunately, these planning algorithms, as I've described them here, are very inefficient. But as we will see later on the course, it doesn't take all that much to turn them into state-of-the-art planning algorithms.